Welcome to our deep dive into ray optics and optical instruments. In this chapter, we'll explore the fascinating world of light, its behavior, and the instruments that help us understand and utilize it. From the basic principles of reflection and refraction to the advanced workings of microscopes and telescopes, this journey will illuminate the science behind everyday phenomena and cutting-edge technology. Whether you're curious about rainbows, vision, or how lenses work, you're in the right place. Let's start by understanding what exactly ray optics is and why it's so important in both science and daily life. Let's begin with the reflection of light. Reflection is the process by which light bounces off a surface instead of passing through it. When a ray of light strikes a smooth surface like a mirror, it changes direction and travels back into the original medium. This simple yet powerful phenomenon is responsible for the images we see in mirrors and shiny objects. Understanding reflection is crucial because it forms the basis for many optical devices and everyday experiences, from seeing your face in a mirror to the way headlights work at night. Behavior of light during reflection is governed by two fundamental laws. First, the angle of incidence. The angle between the incoming ray and the normal to the surface is always equal to the angle of reflection, which is the angle between the reflected ray and the normal. Second, the incident ray, the reflected ray, and the normal all lie in the same plane. These laws are universal and apply to all types of reflective surfaces, whether flat or curved. Mastering these laws helps us predict and explain how light will behave in various situations. Next, we move to refraction, another key phenomenon in ray optics. Refraction occurs when light passes from one transparent medium to another, such as from air into water. As it crosses the boundary, the light ray bends due to change in its speed. This bending effect is why a straw appears bent when placed in a glass of water. Refraction is essential for understanding lenses, prisms, and even the way our eyes focus light to form images. Bending of light during refraction is described by Snell's law. This law relates the angles of incidence and refraction to the refractive indices of the two media. Mathematically, it states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant and equals the ratio of the refractive indices. Snell's law is fundamental in designing lenses and understanding how light travels through different materials. Refractive index of a medium is a measure of how much it slows down light compared to a vacuum. There's a direct relationship between refractive index and the velocity of light in a medium. The refractive index equals the speed of light in a vacuum divided by the speed of light in the medium. This relationship helps us understand why light bends more in some materials than others, and is crucial for calculating how lenses and prisms will affect light. Total internal reflection is a fascinating phenomenon that occurs when light tries to move from a denser medium to a rarer one at a steep angle. If the angle of incidence exceeds a certain critical value, the light doesn't pass through the boundary, but instead reflects entirely back into the denser medium. This effect is the reason behind sparkling diamonds and the operation of optical fibers, which transmit data over long distances with minimal loss. Total internal reflection has many practical applications. It's used in fiber optic cables for high-speed internet and telecommunications, allowing light signals to travel long distances without significant loss. It also explains the brilliance of cut diamonds and is used in certain types of prisms found in binoculars and periscopes. Understanding this phenomenon has revolutionized modern communication and imaging technologies. Mirrors are everywhere, from household objects to scientific instruments. The mirror formula relates the object distance, image distance, and focal length of a spherical mirror. By using geometry and the laws of reflection, we can derive this formula, which helps us predict where an image will form and what its characteristics will be. This formula is essential for designing optical devices like telescopes and cameras. Lenses are crucial in focusing and directing light. The lens maker's formula connects the focal length of a lens to the radii of curvature of its surfaces and the refractive index of the material. This formula is particularly important for manufacturers who design lenses for glasses, cameras, and microscopes. Understanding this relationship allows for precise control over how a lens bends light to form images. Lens formula is another key relationship in optics. It links the object distance, image distance, and focal length for a thin lens. By applying the principles of refraction in geometry, we can derive this formula, which is widely used in designing optical systems. Whether you're working with a simple magnifying glass or a complex camera lens, this formula helps determine where the image will form. Magnification is a measure of how much larger or smaller an image is compared to the object. In optics, it's defined as the ratio of the height of the image to the height of the object. Magnification can be positive or negative, indicating whether the image is upright or inverted. This concept is vital in understanding how devices like microscopes and telescopes enhance our ability to see tiny or distant objects. Calculate the magnification produced by a lens. We use a specific formula that relates the image distance and object distance. This expression helps us determine how much a lens will enlarge or reduce an image. Understanding this calculation is essential for designing optical instruments and for applications in photography, microscopy, and vision correction. Sometimes, a single lens isn't enough to achieve the desired optical effect. By combining two or more lenses, we can create complex optical systems with unique properties. The combination of lenses is used in devices like microscopes, telescopes, and cameras to enhance image quality, adjust magnification, and correct for distortions. Understanding how lenses work together is crucial for advanced optical engineering. Lenses are combined, the system's overall focal length changes. There's a specific formula to calculate the equivalent focal length of a combination of lenses placed close together. This formula helps in designing compound optical instruments, ensuring that the final image is sharp and clear. Mastering this concept is essential for anyone interested in building or understanding advanced optical devices. Dispersion is the process by which white light splits into its constituent colors when passing through a prism. This happens because different colors of light bend by different amounts due to their varying wavelengths. Dispersion is responsible for beautiful natural phenomena like rainbows and is also used in scientific instruments to analyze light. Understanding dispersion helps explain why the sky is blue and sunsets are red. Rainbows are one of nature's most stunning displays, and they're a direct result of dispersion, reflection, and refraction of sunlight in water droplets. As sunlight enters a raindrop, it bends, splits into colors, reflects off the inside surface, and bends again as it exits. This process creates the circular arc of colors we see in the sky. Understanding the science behind rainbows reveals the beauty and complexity of light in our world. Human eye is a remarkable optical instrument. It works much like a camera, using a lens to focus light onto the retina, where images are formed and sent to the brain. The eye automatically adjusts its focus for near and far objects, a process called accommodation. Understanding the structure and function of the eye helps us appreciate how we see and how vision problems can arise. Sometimes the eye's focusing ability isn't perfect, leading to vision defects like myopia, short-sightedness, hypermetropia, long-sightedness, and astigmatism. These issues can be corrected using lenses, concave for myopia, convex for hypermetropia, and cylindrical for astigmatism. Understanding these defects and their corrections is vital for eye care and the development of corrective eyewear. Microscope is an instrument that magnifies tiny objects, making them visible to the naked eye. It works by using two or more lenses to produce a greatly enlarged image of a small object. The principle behind the microscope is to use the objective lens to create a real, magnified image, which is then further enlarged by the eyepiece. This allows us to explore the microscopic world in detail. Telescopes are designed to observe distant objects by collecting and focusing light. The basic principle involves using an objective lens or mirror to gather light and form an image, which is then magnified by the eyepiece. Telescopes have opened up our understanding of the universe, allowing us to see planets, stars, and galaxies far beyond our reach. Light is a form of energy that travels in straight lines as rays. It exhibits both wave-like and particle-like properties, a concept known as wave-particle duality. In ray optics, we focus on the straight-line propagation of light, which helps explain phenomena like shadows, reflection, and refraction. This understanding forms the foundation for all optical instruments. Mirrors come in various shapes, including plane, concave, and convex. Plane mirrors produce images that are the same size as the object, while concave mirrors can magnify or reduce images depending on the object's position. Convex mirrors always produce smaller, upright images. Each type of mirror has unique applications in daily life and technology. The way mirrors form images depends on the type of mirror and the position of the object. By tracing rays and applying the mirror formula, we can predict the size, orientation, and position of the image. This knowledge is essential for designing devices like periscopes, headlights, and even makeup mirrors. Lenses are classified as convex, converging, or concave, diverging. Convex lenses bring parallel rays together at a focal point, while concave lenses spread them apart. Each type of lens has specific uses, from magnifying glasses to correcting vision problems. Knowing the differences helps in selecting the right lens for any application. Just like mirrors, lenses form images based on their type and the object's position. By applying the lens formula and ray diagrams, we can determine whether the image will be real or virtual, magnified or reduced, upright or inverted. This understanding is crucial for designing everything from eyeglasses to cameras. The power of a lens is a measure of its ability to converge or diverge light. It's defined as the reciprocal of the focal length, measured in diopters. High-power lenses bend light more sharply, which is important in applications like reading glasses and microscopes. Understanding lens power helps in selecting the right lens for specific needs. Sign convention is a set of rules used to assign positive and negative values to distances in optical calculations. This helps avoid confusion and ensures consistency when applying formulas for mirrors and lenses. By following the sign convention, we can accurately predict the nature and position of images formed by optical systems. Critical angle is the minimum angle of incidence at which total internal reflection occurs. When light moves from a denser to a rarer medium and hits the boundary at this angle or greater, it reflects entirely within the denser medium. Knowing the critical angle is essential for designing fiber optics and understanding natural phenomena like mirages. Optical fibers are thin strands of glass or plastic that use total internal reflection to transmit light signals over long distances. They form the backbone of modern communication networks, enabling high-speed internet, telephone, and television services. The efficiency and reliability of optical fibers have transformed the way we share information globally. Prisms are transparent optical elements with flat, polished surfaces that refract light. They are used to disperse light into its component colors, reflect light in periscopes, and even invert images in binoculars. Prisms are essential in both scientific research and everyday devices, making them a versatile tool in optics. Chromatic aberration is a type of distortion in lenses where different colors of light focus at different points. This causes images to appear blurred or fringed with color. It's a common issue in cameras and telescopes, but can be minimized using special lens combinations called achromatic lenses. Understanding chromatic aberration is key to improving image quality in optical instruments. Spherical aberration occurs when light rays passing through the edges of a spherical lens or mirror focus at different points than those passing through the center. This results in a blurred image. Optical engineers use specially shaped lenses or mirrors to correct this problem, ensuring sharp and clear images in devices like cameras and telescopes. Convex mirrors are commonly used as rear-view mirrors in vehicles because they provide a wider field of view. Concave mirrors are used in shaving mirrors, headlights, and telescopes to focus light and form magnified images. Knowing where to use each type of mirror helps in designing effective optical systems for various applications. Convex lenses are used in magnifying glasses, cameras, and corrective eyewear for hypermetropia. Concave lenses are used to correct myopia and in devices like peepholes. Each lens type has specific properties that make it suitable for different optical tasks, from enlarging images to correcting vision. Magnifying glass is a simple convex lens that produces a magnified, virtual image of an object placed close to it. By holding the lens at the correct distance, you can see details that are otherwise invisible to the naked eye. This principle is the foundation for more complex instruments like microscopes. A simple microscope uses a single convex lens to magnify small objects. It's ideal for viewing details like the veins in a leaf or the structure of a tiny insect. While limited in magnification compared to compound microscopes, simple microscopes are portable and easy to use, making them perfect for fieldwork and basic scientific studies. Compound microscope uses two sets of lenses, the objective and the eyepiece, to achieve much higher magnification than a simple microscope. The objective lens creates a real enlarged image, which is then further magnified by the eyepiece. This setup allows scientists to observe cells, bacteria, and other microscopic structures in great detail. An astronomical telescope is designed to observe celestial objects like stars and planets. It uses a large objective lens or mirror to collect faint light from distant sources, forming an image that is then magnified by the eyepiece. This instrument has revolutionized our understanding of the universe, revealing the wonders of space. Terrestrial telescopes are designed for viewing objects on Earth, such as landscapes or distant wildlife. They use additional lenses or prisms to ensure the final image is upright and correctly oriented. These telescopes are commonly used for birdwatching, surveillance, and navigation. The resolving power of an optical instrument is its ability to distinguish between two closely spaced objects. Higher resolving power means finer details can be observed. This property is crucial in microscopes and telescopes, determining how much detail we can see in tiny cells or distant galaxies. Optical instruments have limitations, such as aberrations, diffraction, and limited resolving power. These factors can blur images or reduce clarity. Engineers and scientists continually work to overcome these challenges by developing better lenses, coatings, and designs to improve image quality. Photography relies heavily on the principles of optics. Camera lenses use combinations of convex and concave lenses to focus light and form sharp images on film or digital sensors. Understanding optics allows photographers to control focus, depth of field, and image clarity, capturing the world in stunning detail. Lasers produce highly focused, coherent beams of light and are used in many optical instruments. They're essential in applications like barcode scanners, laser surgery, and fiber optic communication. The unique properties of lasers make them invaluable in both scientific research and everyday technology. You've covered a wide range of topics in ray optics and optical instruments, from the basic laws of reflection and refraction to the advanced workings of microscopes and telescopes. Understanding these principles not only explains everyday phenomena, but also drives innovation in technology and science. As you continue your studies, remember that the world of optics is vast and full of discoveries waiting to be made.